So we should go with Phil.
Okay, yeah, thank you very much. So, which means our next speaker is Phil Chipping, and he will talk about the PlasMa project. And what this is all about, he will tell us, and very exciting building. So, yeah, Phil, are you with us? And
I am, yes.
Yeah,
okay.
So, go ahead.
Right. Thank you, Ulrich. Thank you, Peter. This is about as far removed from a C3 as you can get. So, thanks for the invite, and it's very kind of you given the minimum fourth content. But anyway, what is PlasMa? I'll just share the screen now.
Yeah, we see the image slowly building up.
Have we got something there?
Yep.
Okay, right. Well, what is PlasMa? It's a simulator to recapture the essence of an old school mainframe computer system in the comfort of your own home. And this is my blue light version. Just a minute, if I can control over this. The desktop. And this is a red light version built by a guy in Germany. Shows it can be reproduced. And the acronym Phil's Lights and Switches machine was a lucky accident, but it fits the bill perfectly, as you'll see in a minute. Now, my first job in 1973 was in a development hall full of machines like this. Got the engineer on the left, gives you a sense of scale. And we made a range of machines with different engineers' panels. And this was the one I worked on. So if you can imagine, to me, as a young graduate, this was lights and switches heaven. I think I counted 64 lights per row above and below the 3 rows of switches near the top. And these were just the CPUs. And memory was in a separate cabinet. And there was also the operator's console, or OPER, with a low-res text-based screen and a keyboard. There are rows of mag-tape decks and rows of exchangeable disk packs, or disk drives, rather. The disk platters you can see on the top. They can be loaded into the cabinets below. And now, of course, as we've just been talking, computers are everywhere, smaller, faster, cheaper, and a lot quieter. But sadly, in my opinion, they're missing that old school magic. So if you want to re-experience those days for nostalgia or for trying to explain or teach how it all began, you could join a restoration society, but then it's not really your machine, or build your own. And if you replicate a system as opposed to just a CPU, you can also experience the challenges of being a systems programmer in getting it all up and running, and then have a go at being an operator. Now, when I first started work, the system software, the bootstraps, the executives, schedulers, and so on, they'd all been written. So this was something I was keen to revisit. Now, obviously, many compromises are needed for a practical home project. So what do we really need to capture the essence? Now, one essential feature is the hands-on interactive interface, aka the lights and switches. And these are fairly easy to build in hardware, but what about the rest? Well, it had to be simple to stand a chance of getting finished. I'm sure you've all been there with projects. So I restricted it to a batch processing system with a printer. And this avoided multiple user terminals and graphics. So performance was not the big issue, and it could all be implemented in a software simulator. The next question was, should it simulate a real-life system? Well, in practice, pinning down the exact specs for these is quite tricky. And even if you did, they evolved over their lifetime. So which variant would you pick? And in the end, I chose a fictitious system, but combining ideas from various real-life systems for interest. And to make the design simpler, this made the design simpler, but once the system was built, I would not be able to cheat and reach for off-the-shelf systems programs if the going got tough, because there aren't any. But this, for me, made it a far more interesting and challenging project. Right, I'll switch cameras and give you a quick tour around the front panel. Stop sharing. Right. Okay. I hope you can see that. I'll start from the right-hand side. This is the CPU section with all its registers down below on the lights. We've got status lights at the top. From the right, there's the CPU run mode, the stop reason, microcode number, and the FMP flag, which I'll cover later. Then there's some control switches, again from the right. There's run, stop, step, single step, reset, and so on. And the left side is for all the peripherals. We've got the status lights up here for the storage devices. Sorry about the handheld camera. We've got the paper tape reader, paper tape punch, and the exchangeable disk drives. And the mag tapes are down below, the two of them. You've got the status and the tape spools. And then these control switches here, they simulate loading and unloading the media for each storage device. We've got the text-based opera screen here with a simple keypad for a simple input. And then there's a socket on the side, which I can't quite reach around, for an ASCII keyboard. And there's also again, around the side there, is a Centronics connector for a dot matrix printer. That's your system printer. There's a system timer up here, which defaults to the CPU runtime, but that can be program controlled for your own purposes. And we've got the obligatory engineer's key switch, which prevents unauthorized access, and a few rotary controls for this lights, brightness, the loudspeaker volume, and the variable speed clock. And more on this later. Okay, back to the screen. Right, this is inside the box. These are the control switches. And underneath these, we've got the MCU in the middle. It's an Atmega 2560 and surrounded by all the modular PCBs. The main memory lives inside the box and non-volatile storage lives outside using removable SD cards. Now, I wanted the peripheral handling to be realistic, which means no comms links to external PCs or tablets, and certainly no loading files via keyboards or drop-down menus. That would certainly spoil the illusion. And it also meant that each SD card had to simulate a single item of media, regardless of its capacity, which sounds wasteful, but it gives you a true operator experience, having to physically fetch it from the media library, which back then was a climate-controlled room, but now a simple box of cards, and then inserting them into the card sockets at the back of the machine. And these represent the 6 peripherals, and they all run asynchronously to the CPU, just like real life. And this whole approach forces you to experience and appreciate the issues with different capacities and load speeds, as well as the physical hassle of handling media. And as your programs grow in size and ambition, you realize that you have to migrate from simple paper tapes onto more complicated block-structured mag tapes and disks. And that in turn forces you to consider adding features like error correction and file systems. And none of these are available on the basic system. And that's the beauty of having your own blank slate system to play with. You discover for yourself what needs to be done, and you have the freedom to develop it your own way. Now, one final question. If the CPU is fictitious, what architecture and instruction set should it use? I wanted it to be accessible to both beginners and experts. So in keeping with realism, I used a microcode technique similar to the old mainframe. I'll skip the details, but it allows the same lights and switches to be used for different architectures with different levels of complexity. And the beginner's architecture is called Toy, and it's copied from a university computer course with permission. And it has a 16-bit instruction set, 256 words of memory, and 16 work registers. So this was the key factor in the front panel design. Now, bonus was that all the training materials and program examples are freely available, so there's less for me to document. Now, the other architecture is a homegrown one called Plex, which is for more complex programming. The system startup process is the same for all the architectures, and it's based on my memories of the old mainframe. So I'll switch to the camera and we'll try a live demo. Stop sharing. Right, again, apologies for the handheld camera. This switch here controls the FMP flag, which is the force microprogram flag, and it forces the microprogram to be loaded when you run the CPU. And the actual microcode is chosen by setting a number on the top 4 switches over here. So I'll set 1, reset, and run. And the microcode's loaded, and the microcode number is here. Just for confirmation, I can reset the FMP flag, reset the machine, and then the next time the CPU runs, it will start interpreting memory contents as toy instructions. If you load the wrong microcode, the contents will be decoded in a different way with unpredictable results, which is what you'd expect. The memory is volatile, so we now need to load instructions, and this is done exactly as it used to be. There are no shortcuts unless you use Plex, which I'll come on to later. You have to set binary values on the switches. Now, the toy architecture is ideal for mental assembly. Everything is split into 4-bit nibbles, so if you know hexadecimal, it's a piece of cake. Now, there's no time for details, but I'll try and load a small program on the fly to add 2 numbers. I'll use register 1 and register 3 for the 2 numbers and add them together. The first nibble is the opcode, which you may remember from that table I showed you, I flashed up, is a 7. We put a 7 on there. Then the next nibble is the destination register. So I want to load register 1. And then the next 8 bits are the literal value. So I'll put 4 in. I'm loading 4 into register 1. And then load it into memory. The next instruction, I'm going to load register 3 with the value 2. So load register 3, 0, 2. And load it. Now the add is a 1. So we want a 1 here. And you tell it the destination register, which I'm going to put the value back into 3. And we're adding register 1 to register 3 and putting the result back to 3. Load it. And then finally, just for fun, we'll jump back to the add instruction so it loops forever. Now, an unconditional jump is C0. So C0, and then the absolute address. So it happens to be address 2. Load that. Right, we're good to go. Reset, and fingers crossed. Can't read a live demo. I'll try single stepping. And you can see this is register 1. This is register 3. And register 1 has the value 4 in. I'll step. And now register 3 has got the 2 in. Another step, and it's now got the sum, which is 6. And then we'll loop back. and it's gone back. This is PC, program counter. Everything's up, everything's visible. We're under S2, and we go to another add, and there's the result. Now, I don't know if you can hear, every time we do a jump, I'll turn the speaker up a bit. When you hear a click sound, the, where are we? Yeah, this, the speaker was a traditional mainframe add-on, which was connected to the logic such that every jump instruction causes a click. And you soon learn to recognize the sounds of various programs and could even diagnose some problems just by listening, similar to mechanics listening to an internal combustion engine. Now I can run it now using the variable speed clock, just for demonstration. And that's running hands-free now. Turn the clock up. Or I can run it full speed. Okay, I'll just quickly load microcode 3 for Plex. Select, reset, run. Okay, there are also breakpoints and simple I/O with Soy, but I'll move on to Plex now. And when Plex is loaded, microcode 3 now, we've got access to the full set of peripherals, 32-bit accumulator, which is across here, and some flags. And we've got a much richer set of instructions, including floating point, and we've got 64K words of memory. And there's also a small amount of non-volatile memory. Again, no time for details, but just accept that I've already preloaded this with a Bootstrap program. Over here, you can see the magtape spools have lit up to show they're now available in Plex. So I'll try loading a test program from the disk in order to access MT1. And that will demonstrate another feature which is essential for realism, the mechanics of real-life tape decks. Now, I've already fetched the disk from the library and inserted it into drive 0. If I press load EDS 0, the on light has come on. I need to set the switches to tell the Bootstrap to load from this device. I want 2 on there and 80 on here. Right, reset FMP, reset the machine and run. Turn the volume down. Right, the first stage Bootstrap, which was loaded into non-volatile store, is now waiting for the paper tape, which contains a second stage Bootstrap, which loads the test program from EDS 0. Now, I'm still experimenting with Bootstrap techniques. It's a fascinating exercise in logistics. And PlasMa allows you to explore this for yourself in your role as a systems programmer. So I'll load the paper tape, and you should see the on light come on here and the read. And there's the program, the test program running. Again, not very clear, I'm afraid. It's asking for a device to test. Now, I've already got a work tape or a pull tape in tape deck 1. So I'll use the keypad D to tell it to use that. I think everything else is okay. And next we need to tell, or we need to allow the tape to be written to. The default is read only. So I need to fit a write permit ring and then load the tape. Do that now. that's the write permit, and then load it. Now, while that's also threading, I can just tell you that WPR, which is meant to stand for write permit ring, it's not write protect, which is quite an unfortunate use of terminology because it's an accident waiting to happen, as they are completely the opposite meanings. Okay, I'll press B to begin the test. And you can see the write light flashing now as it's writing blocks. And every now and again, the vacuum chamber empties and the discs, the spool motors turn the spools to fill up the vacuum chamber. And that gives you your characteristic twitching movement that you may have wondered about. The rotation speed of the spools also varies depending on how much tape is on each spool. Anyway, I'll stop it now. I'll move on to the final demo. Let me just unload these, unload the disc, unload the tape. Right, this one is more in keeping with the group. I hope I'm not overrunning. Shout if I am. This is just a quick demo of Jones Forth, which I've already put onto MagTape 0. Let me just load it. And what do we want? Put this on the bootstrap to load off the MagTape. So reset and run. Start the paper tape. Fingers crossed, and there it is. That's a relief. Just type in words, say words and page. Clear the screen. Just one thing to note, really, one use of the lights, the parameter stack pointer is in register D, which is this one here. And you can see the current value for all you hex people out there is 3400. Now, if I enter some numbers, I'll enter, well, just put 5 and enter. That's parameter stack pointer has gone down to 33FF. I'll put another number in, 6, and it's dropped down to FE. And if I enter dot to pop the stack and display it, you can see the stacks going back up again. Ooh, and that's the screen result if it focuses. Yeah. Okay, I'm still very new to Forth, so I can't really expand much more on this, apart from showing the ported code, but it's all in Plex, so it won't be very useful. Now, like most programs I've used on PlasMa so far, Forth is just running freestanding and has the machine all to itself. And this is not a realistic scenario, so it'd be interesting to see how Forth fits into a batch processing environment when the executive program is finished. Right, just one final thought to leave you with. I'm not sure if it's possible, but if there was room to write Forth as a microcode, and microcode 4 is next, so it would be very fitting, Forth would be native, in which case all these lights are up for grabs. So what would you use them for? Okay, thanks for listening, and back to you.
Yeah, thank you very much, Phil. Very great presentation, and what an amazing work. I'm sure there are questions, so who would like to ask something about that?
I'd just like to say it's a very beautiful machine.
Thank you.
I'd like one. I don't know whether I've got the time to build one because my wife says I've got too many hobbies already.
Yeah,
it is quite a challenge to build, but it's modular. I've got all the schematics and the PCB layouts on the internet, on the website. I've even got some boards you can buy if you want to buy blank boards and make it up yourself. But you could do it modular, not maybe put so many lights on or reduce some of the switches. But yeah.
How much of the hardware is devoted to lights and switches, and what's for the actual CPU?
There's well, all the lights and switches are just I/O off the MCU. The MCU is the brains of the whole thing. So,
but then it has to have some port multiplexers to get more lights and switches going.
Yeah, let me just show you the inside view again.
Yeah.
So I might be able to explain that. Let's see. Right here is the insert. There we go. Right. If that's come up well, you've got the Atmega in the middle, and that just drives all these boards around the side. You can see there's a chip on, well, the lights boards, for example, the register lights down bottom right. They're in banks of three, like 3 registers per board. And there's a standard LED driver chip that drives, I think these chips can drive up to 64 LEDs. So you've got 3 rows of 16, and then there's 2 extra LEDs per register, which I didn't come on to, but that's 18 per row. So that fits in with a 64. They can drive that easily. So it's standard protocol really for driving those chips from the MCU.
And these are I2C devices?
Sorry?
These are I2C devices?
No. They're just, I think they're Max 7221s, I think, something like that. The only fancy protocol I use is is SPI, I think, for the SD cards.
Okay.
Everything else is bit banged and just done very crudely, but it works.
So what runs the microcode?
The MCU itself, the microcode is really just another route through the firmware inside the MCU. So when you load another microcode, it switches over to using that set of code, I suppose.
Right.
And
Okay.
one set of code interprets the instructions using one architecture, and and so on. So there's a limited amount of room. I've got 3 architectures already in. In real life, a microcode would be loaded off the peripheral, but I couldn't work out how to do that because that would involve loading code and sort of into EEPROM, I suppose, on the MCU at runtime, which is beyond my skill at the moment. So it's all hard coded, as it were, into the MCU.
Yeah, that's an 18 mega, isn't it? I wonder if you could write the microcode in Flash Forth and get that to run the CPU on the mega.
Maybe. I'm sure there's lots of other.
That would be very recursive when you're running Jones Forth on top of it.
Yes, exactly.
Right. Yeah, so lots of opportunities to do that. We can even use Peter's development system eventually to program this device. So this all reminds me when I was a toddler. I was at the computer room where my father worked, and they had an Electrologica X8, very old mainframe. And as a small toddler, all these switches were great, and I touched them, which obviously was not good because the whole system came down. Yeah, anyway, so that's my hands-on experience with mainframes.
Yeah.
And then they never let me close to it again.
I can imagine it would be a disaster, wouldn't it? Toddlers would love those things.
Yes. Yeah.
I have an anecdote to share. I started out at the University of Miami, and they had a Sperry UNIVAC mainframe, and Florida International University, they also had one. And the systems programmer was showing the maintenance panel to his son, and he pressed the LED test light and it caused the system to crash because it used too much voltage, or it lowered the voltage in the machine. So
yeah, I've got a test light on this one as well, and when they all come on, I've had to put a timer on it so it doesn't. It only comes on for a second, just to show that all the lights work. But yeah, it was
the other anecdote was I worked with a guy that the maintenance speaker on the Sperry, when you switched between executive mode and user mode, it would make a sound, and he booted his own operating system that he figured out he could play different notes, and he actually played Bach through the maintenance speaker. So
that's right. Yeah. There
and I've also heard that.
Sorry, I was going to say there's an example of that on the YouTube channel on my on this. I've documented over many videos the progress from right from scratch, building the panels and building it up, and there is a demo in there of a tune made that way. So have a look at those.
I also heard on IBM mainframes they could put radios near the memory, and by playing certain programs in it, you could make sounds through maybe an AM speaker or something. So
that was a standard trick on the Altair 8800. There was a program to play a tune that would be picked up by the AM radio nearby.
You can use it as a debugging device very nicely, because the sound changes whenever your loops change, and so you hear if the program crashed. So very nice.
The interesting thing though is, like in teaching new students, I think it's still important to understand these, like the way you were entering instructions into memory, and then actually single stepping. I mean, it's I don't know if students coming out of college today really understand assembler and how hard. I mean, maybe if they're computer engineers, they do, but maybe basic programmers don't. This device would be an excellent device for teaching.
The guy from Germany who built one, he said he's got a couple of young daughters, and they were fascinated by the lights, obviously just drawn by the lights, but he started teaching them binary. And he said we've had meal times where we were using carrots and celery to do ones and noughts, something to teach them binary. So get them young, it's great.
Yeah. Great.
Bill, I just wanted to ask you. I've got a mate here who was right into ICL, worked at ICL, and did lots of programming and everything else and so on. If he saw something like this, he'd be really excited about it. Have any other friends that have worked at ICL and seen this and recognized it straight away, or been able to use it?
No, it's it's a shame. There's been very little interest, really. So I have put it on. There was an old ICL, ex-worker Facebook group which I joined, and I have tried to promote it on there. But apart from the that's very nice type of comments, and there's no takers. I would really like other people to get involved and maybe write some programs for it, because it's like it's a template really to explore writing your own system software for it. I know it's starting from scratch and reinventing the wheel, but if you keep it simple, I'm sure it's fairly easy to build something up, and it'd be nice to do some collaborations. But at the moment it's a lone.
I can see him being interested in it. That's for sure. Ray Roderick, I think, and then he's been on the forum, maybe. But the thing is that he goes over to England too. He's got family over there, so he might even call in on you.
Right. Well, spread the word, please.
Well, thanks, Phil.
Yeah, Phil. Are there any other questions to Phil? Then thank you very much again. And I think for the first questions you might have, the community support is there. Just ask around, and you will probably get some good advice.
Thank you very much, guys.
Right. So which means our next speaker will be Travis. I saw you already, Travis.